Okay, so now we switch to English. Let me see something. Is this the correct? No. Yes.
Eso, Carlos, no sé si tenía otro tema.
Okay, so here it says Carlos Castillo Juan Pablo Meneses, pero it's just Carlos Castillo. The first lab will be about the Bloch equations. That is something that is a little bit complicated when you start. We also will see how MRI can be applied for fat suppression, and also we'll talk about the T2 preparation pre-pulse that is very commonly used in cardiac MRI. And if I'm not mistaken, it's a question in the coursework one. Okay, so basically what I said, again, let's see the Bloch equations, and as we have already discussed in the extra DA, the Bloch equation has three primary terms. One, that has the cross product between the magnetic field and the magnetization vector that serves to describe the precession of the spins or the rotations of the spins with respect to the main magnetic field, B0. The second term, that it has the T2 or the transverse decay term, and the T1 or longitudinal recovery term. This magnetic field here, B, is a vector that has the principal component of the magnetic field B0. It has the gradients here, G, dot product R, are the gradients times the position in the z direction. That means that we are using this gradient term to the spatial encoding. And if we remember what I said last TA, this spatial encoding is basically changing the frequency of the radio of the tiny water droplets, right? So we can differentiate them spatially. And that frequency that we are changing is basically the Larmor frequency of each spin. And the last term, as you can see here, is the V1, and V1 is usually applied in the XY direction to make the excitation of the spins, or refocusing, depending on the sequence. And the only difference between this box here and the second one is that we are changing the coordinate system. In the first one, we are in the lab or stationary coordinate system, and in the second one, we are in the rotating frame. That means that we are putting our coordinate system that is rotating at the same frequency as the Larmor frequency of the spins. When we do everything in the rotating frame, the equations simplify a bit, but basically they are the same. Here this G is the geomagnetic ratios, but it got messed up when I converted the slides to PDF. But basically the equation here is the same as before, but now we are writing it in matrix form. And this dot that is at the top of the m's are the same as the derivatives that you have here, but we separated the components. So we have now a vector and a matrix times a vector and another vector. Okay, so I didn't show the complete equation with the whole matrix, but these terms that are now 0 are basically the ones that depend on the B1 or the components Bx and By of the magnetic field. So we are now in the case that only has gradients and no B1 or RF pulse. When we remove the RF pulse, these components go to 0, and we only have a decay and a precession within with respect to B0. And this is what I meant when I said that the T1 and T2 are independent, because when you solve the equations, you basically arrive to the conclusion that the set component of the magnetization does not depend on mx or my, and basically you have an equation that is completely independent to the transverse magnetization, and the T2 decay and the precession here is not affected by the changes in the M set or the longitudinal magnetization. Anyone has any doubts for this?
Vale, eso con B8 entonces. Con ETEX, no sé cómo les fue con los temas de entrega, documentación.
If you don't want to use the mic, you can raise your hand or put the question in the chat. But I will continue then. So that's the solution of the Bloch equations when you only have grains, no RF poles. And yes? M0 here is
sí, trata de coordinarla luego porque la
is the equilibrium magnetization is the one that you start basically. When you do not apply any magnetic field for a long time and the signal recovers, it goes to M0 pointing to the Z direction. Yes, MZ is the value of the longitudinal magnetization at time t, and M0 you can think of it as the value of the longitudinal magnetization at time 0.
Y también salía acá, tenía el freo que revisaron si las mantenciones serán horas actuales o nuevas.
Okay, so as you can see here, we still have the dots. So these are differential equations. When we solve them, for the T1 relaxation, we have a exponential recovery where my longitudinal magnetization goes to 0. And then the equilibrium magnetization start appearing with the same exponential decay as this one. So basically, if I have a value of magnetization of 3, this value of 3 starts decaying at the same time as M0 start recovering. So the conclusion or the result is that if you have a magnetization in the longitudinal direction that is smaller than M0, it will recover slowly to M0. I think I have a graph here. No. Yeah, but I have a plot of this, I think in a few slides. And for the transverse magnetization, the equation gets a little bit more complicated. And as you can see here, we now have an I, or imaginary component. And that's because instead of solving two equations, what we are doing is combining them and basically putting a new variable, mxy, that it will be mx plus I times my, as you can see somewhere here, and I think it's not written, but mxy is basically mx plus I times my. And you can, by doing that, combine both equations and only have a complex differential equation. And by doing that, now the equation is a lot simpler. Basically, you have a constant times the transverse magnetization equals to the time derivative of the transverse magnetization, and that's basically an exponential decay. And in the part that you have an I, let's remember the complex exponential that it gives you rotations of an arrow or something. And that rotation depends on the grains. And if we have the assumption that the position of the spins are constant, then the term r, or position that was inside this integral, goes to the outside. And the good thing about that is that we now can simplify this integral by creating a new variable that is called k. And that's why we say that we acquire the images in the k space, because basically we will have that when we do the addition of all the transfer magnetizations, we will have the Fourier transform of the object. And let's remember that the gradients, when you do the encoding, will point to the z direction. Okay, if gx, the gradient that has the potential to encode in the x direction, varies its magnetic field in the z direction. So it adds a component in the z direction, but it varies when you go in the x direction. In this case, we are showing y, but you can understand what I mean. If you see it, for example, here with the z gradient, if you apply a gradient in the direction z, when you move in z, the component that goes to the z direction will vary linearly. That's the point of the gradients. And when you do an excitation, you will get a slice of the subject. That's the main thing of the spatial encoding. So if you apply an RF with a bandwidth, you can capture a slice of a human, like if it was cheese or something like that, and without the need to open the human in real life. Questions about this? Yes, when in the last day, when I showed the tiny water droplets and applied something, and the radius got like different colors. Yes. Okay, so let me repeat it another time. When the water droplets, and the only thing that they feel is magnetic fields. And if we want to change the precession or the local Larmor frequency that they feel, you need to change this magnetic field in the z direction. All the fields here are applied in the z direction. The only ones that are applied in the x and y direction are the RF pulses. That's meant to excite or refocus the spins. And when you change for example, this spin that has that is in my mouse now, it feels this magnetic field, and this one, it feels this other magnetic field. So the first one will have a Larmor frequency of f1, and this one a Larmor frequency of f2. And for example, if I apply my RF pulse with a frequency of f1, I will only excite the first one, not the second one. That's why you can select just a slice. And going back to my illustration with the water droplets with radius, you will change the radius of all of the spins that are in the same slice. And the other ones will be very out of tune, or they will not hear anything we try to say to them. Okay, so let's go a little bit faster so we can do the activity. And the concept of isochromat is basically a spin that rotates in a specific frequency. And when you do an MRI experiment, basically you assume that you have a lot of isochromats after the excitation. And when you want to have the signal, basically what you want to do is to add up all the isochromats. And this is just an illustration of how the isochromats rotate. They will do like a fan, they will open. And if you are doing a spin echo sequence, when you do an RF pulse with an 180 degrees, this will fan out, then they will rotate, and then they will rotate in the opposite direction. And at the echo time, they will all focus again. That's why this is called a spin echo, because all the spins are making an echo. And I'm not sure why this is here. This should be the echo time. And right here, it should be echo time divided by 2. This slide is incorrect. Okay, so this is basically what I was saying. If you apply a 90 degrees and then an 180 degrees RF pulse, basically you'll have your isochromats with the 90 degrees angle. All the spins that are in the longitudinal axis go to the XY axis. They will fan out because you're applying a gradient. That gradient, let's remember, that generates rotations. They will fan out because they have different Larmor frequencies. So this spin will precess faster than this one. Then with the 180 degree RF pulse, basically you're flipping them, but they will still want to rotate in the same direction. So they basically will go together again. It's like when you have people in a circular track and you may all of them run. There will be people that goes faster, obviously, but if you at some point clap and make all of them go back, independent on the speed of each of the runners, they will go at the same time to the finish line. If we do not consider that they get tired and stuff and they always run at the same velocity.
Al parecer no está el adicional.
They are not in the same direction. They are pointing in different directions, as you can see here. Ah, but at the end, yes. At the end, all refocus. Yeah, they are still rotating, but you take the photo at the exact time they all come back together. If you wait it a little bit longer, the spins will spread again. And the good thing about that is that the signal you're acquiring does not depend on the small field inhomogeneities that each spin feels. It only depends on the T2 property of the tissue. When you have a gradient echo sequence, as you can see here, as you do not do a spin echo, you do just a gradient echo, as the name tells us, and the decay of the signal will go with T2 star, and T2 star is faster than just the regular T2. And this T2 star, you can think of it as a T2 decay. It will decay exactly the same. But the reason this T2 star decay exists is because you have a lot of spins that have tiny field imperfections or inhomogeneities. And this is actually what it happens when you do a gradient echo sequence in the scanner. But the good thing about the gradient echo is that you do not need to wait to do a 180 degree pulse and then with TE halves again. So you can do a sequence that is very, very fast. So the decay, it will not be that important. It's not that relevant that you understand this phase diagram, but it's basically the same. The spins will fan out, and then you'll make an echo, but just by changing the precession direction. With a negative gradient, the spins will precess in, let's say, the counterclockwise direction, and then when you have a positive gradient, they will change the direction. And when you have basically the same area that you have here at this point, they will focus and make a gradient echo. And it's important that you understand at least this one, because the gradient echo sequence is the one that you will do in the homework. Okay, so just to summarize, when you have a gradient echo sequence, you make an echo, but just by changing the precession direction of the spins. And as you can see, this tiny arrow is shorter than the one you have in the spin echo sequence, because in the spin echo sequence, you have a T2 relaxation, and in the gradient echo sequence, you have T2 star relaxation. And just a comparison, if you put one and the other at the same time, you have that the T2 star relaxation is faster, and that's why the signal in the gradient echo is smaller than in the spin echo. So if the gradient echo sequence has less signal, why would anyone want to do a gradient echo sequence? Do you know why? Well, the answer could be that your property that you are interested in is encoded in the T2 star decay. For example, if you have tiny accumulations of iron in your tissue, the property that is affected is not the T2 constant, but it's the T2 star constant. And to do some imaging about susceptibility mapping, quantitative susceptibility mapping, for example, is a type of image that strongly depends on the T2 star. So that's why, basically. Another reason is that the gradient echo, you can do it very fast. So, for example, for cardiac imaging, spin echo is not very used because you need to wait a lot of time just for the spins to refocus after the 180 degrees RF pulse. And basically, those are the two main reasons. Probably there's more, but just to tell you that the gradient echo sequence is also good. It's not that the spin echo sequence is the most used sequence. Okay, so I will skip this part about tissue nulling, but the thing I want you to get about this slide is that you can also apply 180-degree pulses in different ways. In this fat suppression example, each tissue has a different T1 recovery. So if you acquire the image when the signal or the MZ component of each one is exactly 0, you can remove completely the contribution of the signal of that tissue. And flare is the fluid attenuation, but the sequence here is the inversion recovery sequence that basically is used to remove unwanted signals based on the T1. And if you want to remove a specific tissue within a specific T1, you need to apply this formula that the inversion time is T1 times logarithm, the logarithm of 2. So this is the most important part of this slide. And another way to do the fat suppression is with a frequency selective RF pulse. I'm not sure if in your homework you have this. I think it's not in your homework, so I just skip it.
De
But
repente se...
you can apply a different technique and also do fat suppression. You can check these slides out afterwards if you want to know more,
Ahí lo dejáis en el flujo
because
LTL, Dani.
it's a little bit
O sea,
complicated.
tiráis lo de...
And obviously you can do
lo que no
weather
hace
selective
por un
excitation
lado y ahí le
directly.
volvéis con eso.
So
Ah, bueno,
you're not
sí.
exciting the fat at any moment. Okay, so this part is important for the homework. When you have cardiac imaging, usually what you do is an acquisition like a spin echo or gradient echo, previously a navigator
Está bueno
to
ese dato,
know
Dani, porque
where the lungs are,
efectivamente, aunque le tiréis la
to,
pelota al
to put
cliente,
it
si no
at the
tiene
same
bien claro
position
qué
every
hacer,
time
se
in
va a
the image.
confundir, se va a demorar y
And
quizás
previous
patee
of
mucho el
that,
procedimiento. Entonces, si
you
podemos
do a
apoyar en ese
preparation
sentido,
pulse.
hacerle más fácil esa revisión,
This could
como
be
mostrándole
T2
qué cosas
preparation,
no cuadran,
fat
dónde está el
saturation, that is
monto, dónde podría estar.
the ones in the
Yo
previous
creo que va a
slides,
salir más rápido
inversion,
ese tema.
and this I think is a magnetization transfer.
Eso.
But the only one that we're interested in is T2 preparation. And the thing about preparation is that you can increase the contrast between your tissues. Okay, so obviously for T2 preparation, you need to know the T2 of the tissues. We will use this in the activity. And for the cardiac muscle, you have a T2 of 50, for fat 100, and for blood 250.
Y bueno, eso con tema de
And you
cuadratura,
have
no
also
sé si ahí tenían vista avanzar
the
con el
frequency
quad
shift of
o
each
esos
one
temas, no sé si se avanzó en
in
la
a
primera
1.5
clase.
Tesla scanner. The frequency shift of fat is 220 hertz.
Quedó listo con la parte también del Power BI
Okay.
y todo.
So the T2 preparation pre-pulse is basically something like this. You have a 90-degree pulse, a few 180-degree pulses, and then a minus 90-degree pulse. And what you obtain is that you can increase the contrast between some tissues. Usually this is done to increase the contrast of the cardiac tissue and blood. And as you can remember, this T2 preparation is based on the T2 of the tissue. That's why it has effect on the image. So with no T2 preparation, the tissues are very similar, but with T2 preparation, you can see more clearly the difference of the blood and, well, the cardiac muscle. I think this was a video, but basically the images increase a lot in quality. Here you can see the T2 preparation of 0 milliseconds. That means no T2 preparation. And the heart is basically a blob. But when you apply the T2 preparation, you can see an increased contrast. Okay, so now for the activity. The first activity we'll do together, and the second one I want you to also open MATLAB and start doing it with me. So the most basic sequence, or this is not even a sequence, but the most basic thing we can do with MR is an FID. An FID is basically applying a 90-degree pulse. And after that, just listen to the signal. Love one.
¿Y esto tiene
Okay.
que ver con esa tabla de pedidos? ¿O nada que ver?
So let's open MATLAB if you can, and go with me. This first activity is just to get you familiarized with the Bloch Isochromat relax function. Okay, so we have this.
No sé si el perfilamiento va o no. ¿No va?
everything that has a percentage sign is a comment and it will not be executed. So the function is basically called like this. You have a v1 component, you have the gradients, the position of the spins, the coil sensitivities that you can just put one. We didn't explain what the coil sensitivities are, but this is also a possibility, and the V0 field that I'm not sure if it's used in any way, but okay, so let's put the V0 as 1.5 Tesla, V1 as 6 micro Tesla. Whoops. Maybe the font is too small for you to see. I can't change it, so let's hope you can read it. Okay, so this is 6 micro Tesla. This is 1.5 Tesla. The gradient, we will not use a gradient here. So the gradient is basically zeros. Let me open the function. So the function here has an example of how to use it. So let's just copy this to do it the same as they suggest.
Entonces, esa sería la actividad
okay, so V1 is an array of nt, that is the number of times time points you want to simulate, and c, that is the number of coils. In our example, it would be just 1. Number of coils, it would be 1. The number of time points, I'm not sure. It depends on how much time we want to simulate. But let's use a time step of 50 microseconds. 50 microseconds. And let's simulate for, 1 millisecond. 1 millisecond. So the number of time points would be the number of times dt and goes inside of t, like this. So that's the number of time points. Okay, so we have the number of coils, the number of time points, and you can also do an array of positions. So the number of spins, let's say is 10. And for the positions, what we'll do is what can we do? Let's say that the x of the spins is 0. Number of spins 1. The same for y. For y. Let's do the same for z. Actually, let's just do 1 spin. Then the positions are x, y, z. Okay, so we have that part, and the coil sensitivities, it will be just 1. Sensitivities 1. Number of spins, like that. And the V0, I'm not completely sure how the V0 is used. Let me see.
Sí, según yo, a mí lo que me explicó es si había que moverlo, que usara esta.
Okay. Okay, so basically, if we want to simulate in the rotating frame, we can put v0 equals to 0. So there's no problem here. So this is the correct amount in reality, but if we are simulating in the rotating frame, we can put 0. So this would be 0, 0 in the rotating frame. Okay, so I think we defined everything already. Oh, we didn't have the grains. So let's define the grains as just zeros. Zeros of number of time points. 1. Gx, gz, and here you have gx, y, gz. Okay, so we have v0, the coil sensitivities, the positions, the gradients, and the v1. But this v1 is not completely correct. This is just the v1 magnitude. If you want to do a correct v1, let's have zeros of nt. Let me check. Nt dot coils. Yes. Coils. Okay, so let's put zeros, and then the first n v1 samples will put v1 magnitude. And how can we calculate the number of samples we want to apply the RF pulse? Do you know how?
Okay. Entonces eso sería...
No?
Eso, no sé si tenía algún otro punto, Romero.
Nobody knows how to calculate the flip angle of an RF field, the RF pulse.
Así que haría las actividades de Almadia. Entonces, no sé si tenía algún otro punto de tu proyecto, Romero.
Okay, so let's do it then.
Creo dejó listo su proyecto. No sé si ahí entramos a revisarlo. No sé qué opinas tú, Stan.
Okay, so the flip angle is the gyromagnetic ratio of the integral of from 0 to t of the v1 of t dt. So if v1 is something like a hard pulse, like in the activity, that is just a square and then 0. That means that is applied for tau with a magnitude of v1. This integral is basically the area of this square. So that means that our flip angle is the gyromagnetic ratio times tau v1. So if we want to know how long we need to apply the RF pulse for a 90-degree excitation, we put a 90 degrees here in radians. By halves is 90 degrees. and that's this
Vale.
tau b1. So to have only tau, you have pi and a half, this tau b1. So that's the amount of time we need to apply this RF pulse to excite the spins with a 90-degree pulse, basically. In MATLAB, that means that tau equals to pi and a half divided by gamma, that we do not have defined yet. Gamma, oh sorry, I put tau again there. Now it's correct. Gamma b1 magnitude, basically that. And we can define our gamma here. Gamma is the gyromagnetic ratio of hydrogen, so that's 2 pi times 42 and 58 e to this, or 2 pi times 42 and 58 megahertz divided by Tesla. Okay, so if we need to apply this for tau, this number of samples would be just the floor of tau divided by dt. Okay, what happens if we run this and set an S? I think we have already simulated. Let me see if I can plot it. Plot figure 1. Plot mx mx yt. Size mxyt.
¿Qué cosa?
20. It's only 20 time points? No, that's too little. Let's put 5 now. Okay, there's more. But I think these variables are reversed. Size mx1. Okay, so you have a and so let's plot this then. Plot this, hold on, plot, and set, hold off. And we simulate them for how long? Sorry, there's something I'm missing because we didn't define the T2 and T1 here. Okay, so we forgot to define the dt of the simulation and m0 and T1 and T2. So by default, it probably takes infinity. Okay, so dt.
¿Cada cuántos días?
Dt is equal to dt m0 equals to 1. That's the initial magnetization. T1. Let's put the same as the one here. For the cardiac muscle, that's 150 microseconds. And T2. And the T2 of the cardiac muscle is 50 microseconds. And I forgot to put this. I'm not sure if it's working or not, but let's see. Because the first one is we are defining the parameter dt of this function, and they are called the same. I defined dt, so this one is that.
¿Y qué cosa? ¿Le pongo la más 7?
Let's see, so if we see now the size of mx, yeah, okay, if I plot it, okay, so now we can see the decays. Let's see this. It's the same. And if I have, you know, 3 spins. Okay, so the size of this one is this.
Anticipo, sí.
Okay, so it's this one without the T. I think they are reversed.
Porcentaje de factura,
But now I'm plotting the correct one. T. Need to transpose this. Yeah, right. Let's just put the one, so it's easier to see. I have a transpose. That does not make sense. There, okay. So maybe I'm simulating too much. Let's put a legend.
Ah, no, está bien.
Of mxy mz.
Eso.
Okay, so
Eso lo estudio entonces.
Let's put a little bit longer t2 to see if it's correct.
Eso. Y bueno, hagamos lo mismo entonces.
Okay.
Ya. Darkmanet.
And let's plot at the same time the RF pole.
Me presenté
B1.
un poco las líneas de acción que consistían, básicamente eran tres líneas de acción correspondientes a SAP, que pues, se conversó y efectivamente solamente nosotros teníamos que ingresar un poco de qué se trata, qué proponemos y qué trata de resolver. No hay que
Let's see, NV1, the number of samples,
de costo ni de
299.
plazo. Quedó claro que al cliente no le interesa, sino que sí aparezca un poco en el plan de acción y que se le dé prioridad.
Okay,
y las otras dos son las propuestas que
se le
envían al cliente, las revisamos con él, le parecieron bien a priori, pero igual le van a revisar a ver si se queda algún tema afuera. Lo que sí me pidieron revisar un tema, que según ellos estaba quedando un poco afuera, y nos vamos a juntar con ellos hoy día para revisarlo. ¿Ya? Es un tema que
so we have our
quieren ver bien
here. And
un tema sobre la planificación de recursos para la producción. No me quedó 100% claro, porque me lo comentaba al final de la reunión, pero decían, mira, este tema creo que nos falta revisarlo, y yo le dije, mira, ya, revisémoslo, quizás no se hizo el énfasis en el medio de la consultoría, pero lo podemos revisar para por lo menos entender de qué se trata el punto y poder...
I'm not sure if I'm simulating it correctly.
Hoy día, de nuevo, con las mismas personas,
I need to double check, but
ese punto.
That's a basic use of this function. I'm not sure if we have time to solve it. So let's leave it like this. Oh, there was a question. Se escucha más.
No significa levantamiento. Mira,
yeah,
la verdad es que
probably end
ahora no me acuerdo bien de
the class here, and I upload a working example later. Okay.